Okie doke, sounds good. So today we're doing two related things. So there's magnetization transfer, which is kind of a transfer between two different pools of protons, and that's you can actually make a magnetization transfer weighted scan. So you can have like a T2 weighted scan or a T1 weighted scan or a proton density weighted scan. But you can also have a magnetization transfer weighted scan. So we'll just try to go over that briefly just to get some general idea of what it is. And then in the second half I'll talk about off-resonance excitation. And kind of like a mental trick on how to think about it, because when you think about the whole block picture, you've got the precessing protons, and then there's a precessing B1 field, and there's relaxation of the T2 and growth of T1. The whole thing is quite a mess, especially when you consider that the stimulation frequency might be different than the precessing frequency. And so there's an easy trick to sort of like get it back to a simple 2D picture. And so that's what we'll talk about that. And this is presented in many textbooks, and it's something that when I first came to it, it's just like I couldn't get what the main point was, and I'll sort of ease you into it. But it's basically just a mental trick in order to make things simpler to visualize. That's really what it's all about. So let's start with the magnetization transfer. So one of the things, this is when you look at an MRI image, you kind of like relate it to to the brain that's actually there, but there's all different kinds of features of the image that are not completely apparent. So an example is if you look at the skull is typically black in an image. And the reason it's black is because, I'll just draw the skull really quickly. So, you've got the skin, and then there's the skull, which is black, and then you see some sort of little white stuff that's all the vascularization in the bone, and then there's another layer of bone. So this whole thing is the skull. The stuff you can see is just the marrow of the skull, like the bone marrow. And then, inside there's the dura, and there's some CSF, which is also black. So you can't tell the difference between the skull and the CSF. And then you've got then here's the brain in there, inside there. So when you look at this image, the skull is black, but that's not because it doesn't have a signal. It actually has a signal. So the air is black. So if you look at the air out here, the air is black, and the skull is black. But the reason the skull is black is because the T2 is so short that the signal is gone before you get a chance to record it. So there's an example of completely different things, like air with no protons in it, skull with skull has a lot of protons in it, it's a big heavy thing, but you can't see it. So we have to consider the effects. So what is magnetization transfer about? It's partly about considering the effects of protons that are decaying away. Their transverse magnetization is decaying away so rapidly that you can't record it, but it turns out it's having an effect, the magnetization transfer effect. So we basically want to distinguish protons that are in macromolecules from protons in water. So if you look at a protein has a bunch of protons in it. It's got hydrogens all over it. So those protons behave differently. So those protons, if you look at there's two ways in which they behave differently. One way is they're not tuned. They have a whole bunch of different resonant frequencies. And what is that from? Some of that's just from the actual chemical structure of the proteins affecting the protons. But there's another so their frequency, so they're not well tuned compared to water. But there's another way that they're different, and that's that the T2 is extremely short. So the T2 of this is like 1 millisecond. So the shortest echo that we typically do on the scanner is like 2 or 3 milliseconds. So pretty much these things are disappeared. Now it's possible with special hardware on the scanner to actually do an ultra short TR. There's a specialized kind of sequence that you can do to actually try to get these, not ultra short TE, sorry, not TR. So there's a special sequence that can do an extremely short echo that's actually under a millisecond, like a tenth of a millisecond. But normal scanners don't do that, and so normally our TE, time of echo, is usually, the minimum is about 2 milliseconds. So these guys just have disappeared. But as we'll see, they're not totally gone. So we compare those with the free protons. In the cerebrospinal fluid, water, blood. And so those guys are the normal protons, where they have a sharp resonant frequency like this. So they all pretty much have the same resonant frequency, and their T2 is more like 50 milliseconds. So it could be less or more, but this is like sort of a lot of brain tissue, a lot of the watery brain tissue will have this property. So these guys are free, and these guys are bound, bound, we'll call these bound protons. Now, of course, there's bound protons in the gray matter too. So it's not that they're, and there's bound protons in the blood because there's going to be proteins in the blood. But there's a ton of water in the blood, and there's quite a bit of water in brain tissue. And so there's a lot of this kind of signal even in the gray matter and the white matter. But both, pretty much everything has both of these. So basically, what is the magnetization transfer? Well, you can imagine it's basically just transferring some kind of magnetization from these invisible ones to the visible ones. So how does this work? So basically, so a pulse sequence that will show you magnetization transfer effects starts off with an off center, off resonance. So off resonance means a frequency that's not this center frequency. Of course, it's on resonance for these guys. So some kind of proton sitting in a protein that has, this particular frequency, that's its on resonance frequency. So when we say off resonance, we mean off resonance for like the big signal coming out of water. So first we do an off center, off resonance RF pulse. And so what we want to do is basically just hit some of these guys, but not any of the blood. So then we wait a little while, wait for magnetization transfer. And so what is that? So we wait for magnetization transfer from saturated. So what does saturated mean? Saturated means you did a 90 and you got rid of all the longitudinal. So from saturated longitudinal of the bound protons, these guys, to the longitudinal magnetization of the free ones. So we're not going to go into the more, the quantum mechanics of this, but it has to do with the longitudinal magnetization, not the transverse magnetization. So what does that do? So what that does is that causes the free ones to be attenuated. So the result of transfer is attenuation. So the signal gets less. So you can sort of think of it as it's somehow penalizing the longitudinal magnetization of the free guys. And so there's less signal when you go to convert it to transverse and record it. So when you look at this, what are the things that immediately jump out at you? Well, when you look at this, you say, like, aren't all pulse sequences like this? And they kind of are. So, if you look, this always happens. So if you look at anytime you do a hard pulse, and so for instance, if you look at a typical anatomical T1 scan, like an MP RAGE scan, you do a 180 and then you do like 100 hard RF pulses, low tip angle RF pulses, like 100 of them in a row in 1 second. So, anytime you do a hard pulse, and remember what the hard pulse meant, like all frequencies. So anytime you do a hard pulse, and like, you're going to be doing like, 50,000 hard pulses in a single anatomical scan, this will happen. Because when you do a hard pulse, it's going to sort of, hit this center frequency, but it's going to hit all the off-center frequencies also. So it happens when you do a hard pulse, but even if you do a frequency selective pulse, it still happens. So if we do a frequency, which is what we were talking about this week, so when you do a frequency selective, slice select pulse. So if we do that, just think of what's going on. So you've got the brain there. Say you want to select a horizontal slice, so you put a gradient on, and that gradient sort of picks out, just the protons that are at that particular frequency for your, for your frequency selective pulse. So you do frequency selective pulse, you turn the gradient on, and then you get like a slice. That's all good. Those guys are just hit just right where they were resonating. But what about these guys? So here's another slice down here. So what's going on with that slice? Well, the gradient was on, and so the gradient changed the resonant frequency of those protons. So there, it changed, depending on whether it's positive or negative, it moved it over here like this. So they're no longer on resonance. And so you can imagine there's some bound protons, and those bound protons are getting hit by the frequency selective pulse, because what's going on is we changed the frequency of all the other slices except for the one we're trying to select. That's how we select it. But when we did that, oops, now we started to hit these much more broad frequency spectrum, resonating at a whole bunch of different frequencies, bound protons in the macromolecules. So the bottom line is you cannot escape. You cannot escape. So it's kind of like the way we said that every image is a little T2 weighted, and it's a little T1 weighted, and it's a little proton density weighted, and it's also a little magnetization transfer weighted. And so that's something you have to think about. Are there ways of kind of suppressing the signal that you're getting from the magnetization transfer? And so it's kind of like these other things. It's always there. It's just kind of a fact of life that we have to deal with. So what is this used for? So you can do a magnetization transfer scan. We have the London pulse multi-echo flash sequence that I got from London when I was working there, has the possibility of doing magnetization transfer, and many pulse sequences on the scanner have the ability to do magnetization transfer weighting. It's not very hard. All you got to do is just add one pulse, because pretty much this part is make image, etc. So here we're just now we just do all the stuff that we do to make an image. And so the only difference is you just have to stick in another pulse. Just the trick is just sticking in an off-center pulse. So you stick in an off-center pulse, and then you've got a magnetization transfer scan. So you probably haven't heard of it. So why do people not do it too much? And so one of the things is it has lower signal to noise. So that's one of the things that, and the reason is because you're kind of attenuating the signal, and you're looking, if you're essentially trying to get rid of the signal from the on-resonance pulse by not even doing the on-resonance pulse, or just doing some small imaging on-resonance pulses, you end up with a noisier image. And so the magnetization transfer weighted image can be a little bit noisier. And so that's one reason why people don't use it as much. If you ever look at, so one of the things you can do with MRI is to look at preserved tissue. So if you look at preserved tissue, it turns out the magnetization transfer weighted images give you tremendous contrast in preserved tissue. So preserved tissue, if you look at T1 in preserved tissue, it's almost flat. So T1 contrast is removed when you preserve a brain. And the reason for that is that when you preserve a brain, what you do is you make a whole bunch of chemical bonds between different parts of the molecules in a brain. And why do you do that? So that the bacteria can't eat it. So it won't. So it makes it completely inedible. You sort of turn it into a gigantic mesh of bonds, so that it's impossible to eat effectively. So what that does is it kind of makes the structure of the brain, the T1 structure of the brain, more homogeneous. And so if you actually do a T1 weighted scan on a preserved brain, there's no T1 contrast at all. The gray and white matter look the same. But it turns out that that MT, standing for, in this case, standing for magnetization transfer, gives you great contrast. And one of the big advantages of a dead brain is that you can get higher signal to noise by scanning it for 12 hours. So there's no, you can easily increase your signal to noise. And so for preserved tissue, and there's a lot of people starting to do this, where they take a whole brain, and rather than sectioning it up, just scan it overnight in order to sort of look at the structure of it. There's a lot of advantages to that. It's a lot easier to just stick it in the scanner for 12 hours than it is to cut 8,000 sections through it and take each one off and stain it and do all the work of that. So there's a growing field of studying preserved brains. Okay, and there's another thing, one last thing that magnetization transfer is commonly used for, that you'll see on the scanner, and this is called a time of flight scan. So yet another kind of scan, yet another kind of weighting that's in. So we've got like we're just building up all the weightings. We got T2 weighted, T1 weighted, proton density weighted, magnetization transfer weighted. And so you have another weighting that comes from the fact that not all the spins are in one place. So this all has to do with moving spins. And the simplest way to think about it, so it turns out every scan is weighted by the distribution of moving spins. So if you just take a T1 image and look at it, and look at the carotid, if you look at the carotid, it's always bright. So why is it bright? Is it bright because, it's really bright? I mean, like intensely bright. Is it bright because the T1 is super short there? And no, the answer is no. That's not what's causing it to be bright in the T1 weighted scan. What's causing it to be bright is that you're imaging away at the head and the neck, and so you're saturating these spins, and so you're kind of distressing them by constantly tipping them, and you've got your longitudinal magnetization going down because of your constant hammering at them, and then you've got some blood zipping up from your heart, and that blood hasn't been saturated at all. The protons in that blood haven't been saturated at all, and so they come into the slice, and they've got all these tired protons in there that have been all saturated, and their magnetization, the longitudinal magnetization was reduced, and then you've got some fresh ones flowing in there that haven't been zapped yet, and those guys will be brighter. And so you can use that fact. There's various ways to try to emphasize that, but you don't even need to do anything. All you have to do is just do a T1 weighted scan, and because of the fact that there's going to be, because you're hammering away at this part, so these guys are all, saturated longitudinal magnetization, but you've got some, blood coming in, and that's got some nice unsaturated blood powering in there, and when that blood gets up into the slice, there's going to be some nice fat longitudinal magnetization that will give you a big signal. So that's yet another kind of weighting. And I won't go into the details, but there's various gradient tricks that you can do to try to emphasize the moving scans. And what do these scans look like? So if you've ever seen a picture that just looks like an angiogram, so you can just see, like the carotid blood vessels like that. It just looks like you just see these, blood vessels, circle of Willis. So you basically just see the blood vessels. So, and then you can animate this, to turn it around so you can see it in 3D. There's a very simple trick on how that animation is done. So if you take a block of voxels, and those voxels have some blood vessels in them, say, here like this, some bright blood vessels. Rather than trying to actually reconstruct the blood vessels, a simpler thing is just make lines that go through the image. So here's the back of the cube. So just make lines that go through the image. Here's one that comes out here. And for each line going through the image, just find the brightest voxel. So that's called a maximum intensity projection. So all you do is you just draw a line through the image, find the brightest voxel, you're done. And then make an image out of that. So just make a 2D image out of that. So what you end up with is just a 2D image, and then you see blood vessels in it. But that's not animated. So how do you animate it? Well, just rotate your lines a little bit, and do the same thing. So instead of running the line straight through this way, run them slightly out at you like this way. So do exactly the same thing. Calculate another 2D image, and if you just rotate slowly, what you'll get is something that looks like you injected contrast into all the carotids coming up, and you'll see you can see the blood vessels just rotating around, and you can look for problems there. And what kind of problems do you get? Well, if your carotid has like a little bend in it, sometimes, and you eat too much rich food, you get a little crud building up right in that bend, and that's the main blood supply for the side of the brain. And so and if the crud builds up too much, it can really restrict the flow. So I always tell the students, eat more plants. It's always good to eat more plants to stop that, keep that clear. But that's the kind of thing you would look at with this kind of picture. So it's a very quick and dirty way of making a 3D image, a convincing 3D image. You can just see the blood vessels just rotating around in 3D, and all you have to do is just find the brightest pixel on a line. That's maximum intensity projection. So that's one. So that's time of flight. But how does magnetization transfer relate to this? Well, it turns out that that MT can suppress signal in rest of brain. So it just increases. It's a way of increasing the contrast, so that you can actually see the blood vessels even brighter, so that when we do this maximum intensity projection, we just get a clearer picture. So that was the magnetization transfer. So we've got these two different pools. You can sort of conceptually, there's more pools than this, but we can sort of conceptually think of bound protons that have this broad resonant frequency and a very short T2, and then free protons have this sharp resonant frequency, and the T2 is much longer, like 50 milliseconds. And so what is magnetization transfer? You just do an off-center RF pulse, and then wait for some of that longitudinal magnetization to get transferred somehow to the ones that you can actually record, with the effect that it attenuates it, and then you make an image. And we won't go into the details. You make an image the standard way. And what will happen is, in places where a lot of transfers occurred, the image will be darker. So like in this case, for the time of flight, we don't want the non-blood vessels to appear, and so we kind of suppress the signal from the whole rest of the brain. Okay, so that was magnetization transfer. So now what we want to do is try to understand the off-resonance excitation idea, because this is what we're doing here. We're doing off-resonance excitation, and what's a way of thinking about that we can jam into our primate brains in a way that we can sort of see a little picture. So the idea is has to do with the rotating coordinate system. So we've already been doing this. So the thing is, whenever we talk about, we've already been doing this. So whenever we talk about sort of, we've got some magnetization here, and we flip it down, to that point, and then we calculate, how much transfers we have and how much longitudinal we have. We're already in the rotating coordinate system. So that already is the rotating coordinate system, because that that vector is not rotating, it's just stationary. So we've already been sort of intuitively doing this. So all we want to do is add here, what does that vector look like when you've got some off-resonance going on? So if we sort of conceptually go over the stages of simplification. So when we first started off, we had, when we were talking about the block equation, we had the B field here, and then we had our local magnetization vector, and that was precessing around. So when we calculated our change in the magnetic field vector as a function of time, it causes precession. So that's our starting point. So so when we go to the rotating frame, that's rotating around the same speed, what happens? So I'll draw that guy again down here. So in the lab frame, what we see is, here's the lab frame. We have some magnetization vector and some B vector, and we're basically precessing around like that. So that's the lab frame. Now, when we first go to the rotating frame, what happens is we stop that vector. So remember, over here, this is, we were just thinking of, B0, and we had no B1, because the B1 was an additional transverse part added to the B vector, so to cause the B vector to wobble. So when you do an RF pulse, effectively what we're doing is we're sort of saying we've got a big B vector, but we've added some transfers to it, and when we add the transfers to it, it just causes this big B vector to wobble, and then that's what actually weirdly causes this magnetization to sort of head down to the transverse plane. So that was the lab frame. But if we go to the rotating frame, and we hit the resonant frequency perfectly, what's going to happen is our I'll draw that one in a different color. The magnetization vector will just stop in its tracks. So this is the magnetization vector now. So it just stops if we if our rotating frame hits the actual precession frequency of this particular proton exactly. So now we're just completely stopped. X, Y, Z, Z, X, Y. So now let's consider what happens if we do a B1 in the stopped case. So this rotating frame, so what's happened here? Well, M has stopped. And what does that mean? That effectively means B0 equals 0. So we've sort of canceled out the B0. So here we have actual precession, and B0 is, equal to B0. Now when we go to the stop frame, we've essentially sort of zeroed out B0 so that there's nothing causing precession, so the magnetic field vector just stops in its tracks. So now what happens when we add B1? Before we do off resonance. So now if we just add B1, what happens? Well, then what we do is you can think of this as the same thing as precession, but now rotating around a different axis. So now what we have is we've got our B. So in this case, what is the B vector? So the B vector, just equals 0. It's not there at all. It's nothing. So when we add B1, our B vector, so here's B1, our B vector is now pointing along, in the XY plane someplace. Could be somewhere else, depending on the phase, but let's just say it's along the x-axis. So what about our M vector? Well, our M vector is still there. So now what's going to happen? We're going to get precession around the B vector, just like this case. So we're going to get precession around the B field, just like in the precession case, except now the B field's along the x-axis. So the trick is you can sort of think of a flip just like a precession. Now that we've zeroed out, so what have we done? Well, so the M. So the first thing is that the B1 is also stopped. So in this case, the M was, rotating around very rapidly. Now we stopped the M when we went to the rotating frame, but we also stopped the B, assuming that we did an on-resonance excitation. So the M is stopped, the B is stopped. So in real life, they're both whipping around really fast, but now they're stopped. But now we can sort of consider a flip as if we were causing the M to precess around the B1 field. And so what does that look like? Well, that looks like basically a rotation, same kind of rotation that you would get, here. So this thing is, just think of this as that. And how do you calculate that? Well, you actually use the same equation. It's just the block equation. So it's basically just, the change in the magnetic field vector as a function of time, just, equals the m vector, which is this guy, cross-producted with the b vector. So the only component of the b vector is the b1 field, because we got rid of the z component by going to the rotating frame. And so now it just causes this guy to rotate. And so this one will basically just precess slowly. You can sort of think of it as precessing slowly around the b1 field. So that's a flip. So now we've sort of conceived of a flip as just another kind of slow precession. Okay, so that's all good. So now the final insult, we have to sort of consider what happens when we're doing something in an off-resonance case. So what happens when you do something in an off-resonance case? So now it gets a little more complicated. There's more arrows. So I'll draw it out here, and then I'll draw sort of above and below off-resonance in a second, but we'll just start with this. So what happens off-resonance stim, RF stim. So what happens when we're off-resonance? So first of all, let's just take one off here. What does off-resonance look like? So if we do an off-resonance, if we get our rotating frame wrong, because we essentially have not set our rotating frame to the same speed as the actual precession, what will happen? This vector will start to move. So the m vector will start to slowly move around. What is that equivalent to? That's equivalent to some bz. So it's some apparent bz. So if off resonance m slowly precesses as if bz, small bz, as if small bz present. So anytime we're off resonance, it appears as some z component of the field causing a precession, a slow precession, because we're almost on resonance, we're just a little bit off. And so what does that do to our flip here? So what it does to the flip is, let's draw a more complicated picture now. So now we've got our m vector, just like we had it before. So here's our, let's try to draw it the same as before. There's our m vector. And then here's our b1 vector. That's the same one as before. But now we have a fake bit of sort of apparent BZ. So this is apparent BZ from off resonance. So what does that do? Well, that's just That's just something that kind of adds on to the B1 field. And so now we have a new B vector, and we call that B vector B effective. So that's a B vector, B effective. And so basically what's going to happen now is we're going to rotate this guy around B effective. And so what is that going to do? Well, before, when we did the cross product, we ended up with something that was just aiming toward the y-axis. It's just exactly aiming toward the y-axis. And what is that? That's perpendicular to the, so it's rotating in a plane that's perpendicular to the B field. But now our B field, our B effective field, so here's B1 and B effective, is now tilted. So what that means is that this guy is now going to precess slowly from our off-resonance stimulus in a plane perpendicular to this tilted guy. So it's sort of going to come out at you like that. Sometimes you'll see in drawings in textbooks, a little circle like that. Less with like if you imagine a smaller M vector. But basically what's going to happen, instead of just sort of rotating around the ZY plane, aiming toward the y-axis, what's going to happen is it's going to come out. It's going to come out because of this tilt and rotate around a plane that's not right in the ZY plane. So that's kind of the way to essentially turn everything back into a simple picture that we can understand as a monkey, which is we've just got a B field and an M field, and we just do M cross B to figure out which way it's going. And which way is it going? It's going to be going in a plane. It'll be rotating in a plane perpendicular to the B. So that's what's happening here. So we've got the B1 field, and then we have a fake BZ because we were from off resonance, and that causes the effective B field, same as this guy, to tilt up. And then as a result of that, when we do our RF stimulation, we're going to get a different precession plane than we would if we were just essentially precessing around the B1 by itself. So that's the off resonance idea. So the first time you see it, it's just like, why do you go through all this trouble? You said extra vectors. Because it's actually better than thinking of, the wobbling B0, in a precessing frame. That's even more complicated. You've got like precessing protons, and then the B field itself is wiggling, maybe at a different frequency. There's too many things to keep in mind. This is kind of a way to simplify it back down to a simple precession. So that's the reason that you want to do this. So let's just draw up one equation and that will be done. So this is the equation for the B effective. So here's the B effective. So there's several things in it. You might have noticed that a gradient changes the BZ. So a gradient will do this too. So there's three things here. So the first, I'll put so we'll start off with how far off we are from the resonant frequency. So that's the off resonance term. So that one, and why is it sort of frequency divided by this? Because you remember the original thing was, frequency equals this times B And so basically what, B equals, equals, frequency divided by that, right? So this guy is B. So that's why you're dividing by the gyromagnetic ratio. So, and then this guy is in the Z direction. That's the Z direction. Okay. But a gradient can do the same thing. So because remember the gradient just changes the Z component. So whatever the value of the gradient is, that's also added in there. Because if you, like for instance, when I was talking about magnetization transfer occurring because you put a gradient on, that changes the resonant frequency. So that's another thing that will move this effective B field around. And then finally you have the one that we already know about, which is basically B1. Yeah, so here's the actual RF. So this is a real thing. And for now we're just talking, we were talking along the x-axis. So that's why I put the I there for x. So whereas K is Z. So you'll see this equation. So what that says is that when we consider this more complicated, realistic situation, we have to consider how much off resonance, how far are we off resonance? But then we also have to consider, like, is there any gradient on? Because that's actually going to move this effective B vector around. And then finally we have to actually consider something. So you can sort of think of these. Well, that's a real thing. We actually turn the gradient on. This is kind of this fake thing from being off resonance. This is something we turn the gradient on, and this is something we turn the RF on. Okay, so we'll finish there, the final insult, and take some questions. Okay, sorry, David.